let me do that formally. Okay. So this was the bound that we intended, right? So Sn greater than n p tilde. So where Sn is
Sir,
summation.
so we can't
Hello.
see your screen, sir.
Oh, I'm sorry. I'm sorry. I think I didn't even share. This is something that I do all the time. Okay. So can you see now?
Yes, sir.
Yes. Okay. So this is, we were looking for a bound, an upper bound on this probability, right? This Sn is summation over all I xi, where xi is a Bernoulli random variable taking values in what? 0 and 1, right? So this was the problem. So what is the upper bound using Chernoff, right? Okay. So let's see how to go about doing this. So let's supply the usual Chernoff. So the Chernoff bound says this is infimum over all, let's say R greater than 0, right? Expected value of e power, what is that? R Sn times e power minus R n p tilde. Is that fine?
Yes.
Okay, so now let's look at this particular thing. So maybe I'll just work out what this is. Okay, so this is basically expected value of e power Rsn, which is nothing but expected value of e power R summation over all I from 1 to n xi, which is nothing but expected value of product. Exponential of sum is the product of exponentials, e to the power R xi. Now you should tell me why this is true. Why is this true?
Because they are
Independent,
dependent.
independent, sir.
They are
As
independent,
independent.
right?
Yes.
So if you have independent random variables, expected value of xy or g of x, g of y would be expected value of x times expected value of y. Okay, so it's easy to prove using the definition of the expected value. Okay, so now this is equal to expected value of e to the power r x1. Why is this true?
Because they are identical.
IID, sir. IID.
IID. So they have the same distribution. So all the expectations will be same. So it's power n. Okay. So what is this? This is x1 can take 0 or 1, right? So it takes 1 with probability p. So if it takes 1, you have e power r plus it takes. Okay. So now let me use q for 1 minus p. So it takes 0 with probability q, right? This is what we have. Do you agree? Is this
Yes, sir.
fine? This is simple, right?
Yes,
Now
sir.
let's substitute that back into the previous equation. So I get probability of Sn greater than n p tilde less than or equal to infimum over all r greater than 0 p e power r plus q whole power n e power minus r n p tilde, right? So this is what we need to do, right? Now, let's do the usual stuff. So in fact, one can show that this is convex provided P tilde is greater than P. Okay, so then it's convex. In that case, I can find a unique minima, which you can obtain by simply differentiating, right? So differentiating this, let's differentiate. So what do we get? Of course, differentiate with respect to R. So if we differentiate, we get n p e power r q whole power n minus 1, right?
Yes.
Is that correct?
No, sir. There will be this term also, no, sir?
Okay, so now let me just do the following. So I'll rewrite this as, okay, so let me take this back. Okay, so let's not do differentiation directly. I'll write this in a slightly different fashion. So I'll write this as infimum or all greater than 0 Okay, exponential of ln of n ln p e power r plus q minus r n p tilde. Okay, is this fine? Okay, x I can write it as e power ln x, right? Because e and ln will cancel and you get x. That's what I have done. Is that okay, everyone?
Yes.
Everyone?
Yes, sir.
Yes,
Okay.
sir.
Okay, fine. So let's continue. Okay, so now I want to take the infimum of this, or I can do exponential of minus r n p tilde. Sorry, I can do supremum or all r greater than 0, r n p tilde minus, okay, I can also pull n outside, right? So I'll do n here, r p tilde minus ln of p e power r plus q. Is that fine? This is your Chernoff bond, right? All that I have to do is to essentially find the supremum of this function. So in order to do that, we differentiate with respect to r. So what is the derivative of this with respect to r? It's p tilde, right? Minus, yes,
1 over p e to the power r
yeah. So
plus
it's
q
1 p e power r plus q,
into
right?
p.
Into
P
p e power r, right?
power r, yes, sir.
Is equal to 0, right? Okay, so you can solve for r from this. So if you solve for r, what do you get? So I can write, for example, e power r. If we solve this, it's p tilde q divided by p q tilde. So q tilde is 1 minus p tilde. Okay, so q tilde is 1 minus p tilde. Okay, this is what we get. Okay, so now whenever p tilde is greater than p, okay, so we have differentiated this and equated it to 0, right? So I want this function to be, so we are finding the supremum, right? I want this function to be concave, something like this, right? Then if I differentiate and equate it to 0, I get this point, which is the maxima, supremum, right? So when will this be concave? You take this double derivative of this with respect to r. What is it that you get? So you have to take the derivative of this function with respect to r and see what is the answer. Okay, it turns out that whenever p tilde is greater than p, this r is, you have a valid r for r greater than 0 will be a solution if p is greater than p tilde is greater than p. Okay, so if p tilde is greater than p, r is greater than, or r star is greater than 0, which leads to, okay, I can just substitute this here. It gives me the following. Okay, so it gives me, this whole thing will give me what? Probability of Sn greater than np tilde is less than or equal to exponential of minus n, the Kullback-Leibler distance. Okay, so where this Kullback-Leibler distance p tilde and p is defined as p tilde ln of p tilde divided by p plus q tilde ln of q tilde divided by q. Okay, so this is your Kullback-Leibler distance. Is that fine? So it says that this probability goes exponentially down to 0 as n goes to infinity. Is that okay? This is one simple application of Chernoff bound that we started looking at it in the last class. Okay, but it turns out, this is an exercise problem anyway. It turns out that you look at probability of Sn greater than or equal to np tilde. Okay, so you take the natural logarithm of that and divide by n and take limit n tending to infinity. Okay, this will be, so if you apply the same thing here, you get minus Kullback-Leibler distance, right? It got stuck. What happened? Hope it's saved. Okay, good. Oh, it didn't save the last part. Okay, so it turns out limit n tending to infinity, ln of probability of Sn greater than np tilde divided by n is the negative of the Kullback-Leibler distance between p tilde and p. Well, from this we can conclude that the left hand side is less than or equal to the Kullback-Leibler distance, minus Kullback-Leibler distance. But if you have to, if this equality to be hold good, then you need the reverse inequality as well. It should be greater than or equal to minus bp tilde np. Okay, is that fine? So this is one application of Chernoff bound. You can find many such useful scenarios where you can use Chernoff to find interesting bounds on the probability of some large deviations. Okay, any questions so far? This is very important. Okay, so the same technique holds good for other cases also. Okay, maybe let's do one more. Let's try. I didn't prepare for this. Let's try one more. Okay, suppose. Okay, this is an example. Maybe this is quite useful. Okay, so let's look at x1, x2, etc. or IID Gaussian, zero mean and variance sigma square. Then probability of, I want to look at I equal to 1 to n xi. Okay, greater than something. So let's assume some epsilon here. Okay, epsilon greater than 0. Okay, so now I want to prove a bound on this. What do? I'll just apply Chernoff, right? So what will be the Chernoff inequality? It will be less than or equal to infimum over all r greater than 0, expected value of e to the r summation I equal to 1 to n xi e to the power minus r epsilon. Same old stuff, right? No changes. Now I have to compute this expected value, right? So this expected value of exponential of the sum is the sum of product of the exponential, right? So I can write this as product. So this is expected value of the product is the product of expected value. So you get e to the power r xi, right? This is same as expected value of e to the r x1 whole power n, because it's IID, right? Same stuff. Only deviation would be computing this. So what is expected value of e power r xi? x1, which is nothing but integral minus infinity to infinity e power rx, the density of x dx, right? Expected value of g of x is integral g of x fx of x dx, right? So this is what we have. Is this fine?
Yes.
So this would be minus infinity to infinity e power rx. What will be the density function? Did I talk about the density of a Gaussian random variable? Oh, I think I didn't mention this, right? So, Sumit, you know, and others, you know what this is?
Yes, sir.
Yes, sir. I just
What is this?
Yes, sir.
Yes, sir.
I said Sumit because you might not have seen this, but others are from engineering background, so they would have hopefully seen this before. Sumit, you are aware of this or no?
yes, sir. I just read it in book, sir.
Okay, so it has the following density. Okay, so I'll just write it: e power minus x squared by 2 sigma squared dx. Okay, so now I can combine this. So this is what e power minus of x squared plus 2x sigma squared by 2 sigma squared. What I can do is, see, you have x squared here. I'll add sigma power 4 and subtract sigma power 4 here. Fine. Completion of square. So what will be this? This will be x plus sigma squared whole squared, right? Is that correct? Fine, everyone? Hey, did I miss R here? I missed R, right? X squared 2x sigma squared R. Right? So sigma squared R is something that we have to, okay? Add and subtract something, right? So now what do we have here? This is 1 by root 2 pi sigma minus infinity to infinity. The first term will be exponential of minus x plus sigma squared r whole squared divided by 2 sigma squared dx, because that's the only term that depends on x, times I have to pull this out, right? Exponential of sigma power 4 r squared by 2 sigma squared. Is this fine, everyone? I'll pause for a minute. Is that okay? I'll just connect my laptop to the charger. Meanwhile, you can think, and if you have any questions, you can ask. Any questions? Any questions? No? No questions?
That is x. So you write x square plus 2x sigma square or sigma r square?
Sigma squared r, right?
Okay.
I'm just completing the square. Okay.
Sir. Okay.
Okay. So this is just a completion of square, and this is the other term is independent of x, so I have pulled that out. So what can you say about this thing now? So what can you say about the integral? Can somebody?
Shifted. So mean is shifted to sigma squared r. So because in normal distribution we write the PDF like x minus mu whole square divided to sigma square.
Okay.
So its mu is replaced by minus sigma square or something like that.
So mu is in this case what?
Minus sigma square r.
Right. So it's again, this thing is nothing but integral of a Gaussian PDF with mean minus sigma squared r and variance
Same, sir. Sigma
right?
square.
So this will be what then? Integral of this would be integral of Gaussian. I'll just write this as a simple notation: minus sigma squared r squared sigma squared dx. Okay, you know what this is? This is a Gaussian PDF. What is this? Into
1.
It's 1, right? Sigma power 4 r squared by 2 sigma squared. So this is 1. So what do we get? So we get exponential of minus or plus sigma power 4 r squared by 2 sigma squared. Okay. This is something that we need to substitute it here, right? So this stuff, right? Shall we do that?
Sir,
Ah,
sir, can you please repeat, sir? I just lost the connection, sir.
okay. So
Just
from here,
yes, sir. From the yes, sir. Where do you just write the distribution function, sir? Density function, sir.
so I'll just write. Maybe I'll just go back and write. So I'll just write it here. This is an aside. Maybe I'll use a different color. So X is distributed as Gaussian with mean mu and variance sigma squared if the density would be 1 by
1/√2
sigma exponential of
exponential.
minus x minus mu whole squared by
Yes, sir.
2 sigma squared.
2
So
sigma
since
square.
this is a density function, if I integrate the density function from minus infinity to infinity, we'll get 1. Well, you can
Yes,
take
sir.
that as an exercise, right? And show that it's 1.
Okay, sir.
So if you look at this, right? See this particular term, right? This is nothing but the density of a Gaussian random variable with mean minus sigma squared r and variance sigma squared. So
Sigma
it's a
square.
density function. So I'm integrating a density function, right? So I'm integrating a
Oh,
density function. So I should get 1. So the remaining term will come here.
okay,
You wrote
sir.
R square in the place of mean. It's a slight typo in the
Right?
mean. So n of
There is no r
yes.
squared. Oh, there is an r squared here. Okay. So
Yes, sir.
now probability of summation I equal to 1 to n xi greater than epsilon is less than or equal to infimum or all greater than 0. I'll get this exponential, right? This is exponential of, okay, sigma power 4 r squared divided by 2 sigma squared. That's the first term. The second term would be, well, this power n, right? So there is an n also here. Okay, why is that? Yeah, because of this. Expected value of a Rxi is what we have shown. That power n is also there. Minus R sigma, right? Minus, is there an n there? No, right? Sorry, R epsilon. Is that correct? So we have minus R epsilon. Is that okay?
Yes, sir.
This is nothing but I can do the following, okay? Minus, I'll take minus out. If this is infimum, it should be supremum or all greater than r greater than 0. So this term would be what? R epsilon minus n sigma power 4 r squared by 2 sigma squared. So this, now I have to solve for the other term, right? Okay. I have to solve for the other term. So basically I have to solve, so take supremum over R this. So what will be the answer? Let me call this as f of R. F dash of R would be epsilon minus
n sigma to the
2n
power 4
sigma power 4 R divided by sigma squared.
sigma
Right?
square.
Why am I writing sigma squared and sigma power 4? So I can just do 2, right? So equal to 0. So what is R? R is epsilon
By
divided by
n
n
sigma square.
sigma squared, right? This is what R star would be. So now substituting that there, what do we get? It's exponential of minus R is what? Epsilon divided by,
N sigma square.
hey, is this correct? Yeah, I think it's correct. Okay. Epsilon R is epsilon squared divided by n sigma squared minus what? This n sigma squared r squared by 2, right? So this is nothing but n. Hey, did I make any mistake here? Okay, so is this supremum? Yes, it's supremum. This is also correct. Let's see. So n sigma squared, r squared is what? Epsilon squared by n squared sigma power 4, right?
Yes, sir.
There is something wrong. You see anything wrong here? Sigma power 4 r square by 2 sigma squared. So this will be sigma squared r squared divided by 2. So I'll just write this neatly. Sigma square r squared divided by 2. Right? This is what we have. Sigma squared r squared divided by 2. This is also sigma squared r squared divided by 2. Right? Now this will be n sigma power 4 r squared sigma squared divided by 2. So this will be n minus r epsilon. So this will be supremum r epsilon minus n. Okay, so now okay, fine. So let me write this. This is epsilon squared divided by n sigma squared. Okay, and what will happen to this? This will be sigma squared epsilon squared. Oh well.
Epsilon square by 2 n sigma square, sir.
Epsilon square by 2n
sigma square.
Sigma square.
So what will be this? This is exponential of minus epsilon squared by n sigma squared minus this will be epsilon squared by 2n sigma squared.
Sigma
You
square.
agree? Now suppose I take epsilon. Suppose epsilon to be, let's say n. Okay. Suppose epsilon is n. Right. So what is the problem that we looked at? This summation is greater than epsilon, right? Suppose epsilon is n, right? So let's look at what happens. So then probability of, I'll write it in a slightly different fashion. Xi greater than epsilon would be less than or equal to exponential of minus n divided by 2 sigma squared. That means it goes, this probability goes down to 0. There should be an epsilon squared. Okay. Sorry, epsilon is, okay, so let's not just use n. Epsilon is n delta, okay. Delta squared divided by 2 sigma squared. Is that fine? So that essentially says that if you take epsilon to be n delta, this is delta, right? So what is this result saying? Can somebody interpret this result for me?
Sir, mean will be greater than equal to this, like the average of those random variables with greater than delta has an upper bound this.
Correct. Yeah. So then, of course, this delta is greater than 0. That's the assumption.
Yes.
So that means this is an estimate of your mean, right? If I give you n samples from Gaussian distribution, the mean is given by this, right? Now, the true mean is 0 in this case. Expected value of x1 is 0 or xi is 0. So this is saying if you compute an estimate of the mean using samples, n samples, that being greater than any small number delta is upper bounded by exponential of minus n delta squared by 2 sigma squared. Essentially, it's saying as n goes to infinity, this goes exponentially down to 0. So suppose, let's take an example. Okay, so example of this. Suppose I want delta to be 10 power minus 4. Okay. Okay, and I want this average to be let's say probability of this average 1 over xi greater than delta to be smaller than, let's say, eta, zeta or whatever, right? Then if I want this probability to be less than zeta, if I ensure that this upper bound is less than zeta, I'm done, right? So then exponential of minus n delta squared divided by 2 sigma squared is less than zeta. So what does that imply? If I take ln on both sides, n delta squared by 2 sigma squared is less than ln of eta. Well, eta is less than 1 and 0, okay? Greater than 0. So this implies n delta squared by 2 sigma squared is greater than or equal to ln of 1 by zeta, right? I'm just swapping the signs, so that's all. So this implies n is
Sir?
greater than, just 1 second, delta squared divided by ln of 1 zeta. Okay, yes, tell me.
Yes, sir. Actually, so this one you have taken, no, sir. Probability of the average greater than equal to delta is less than zeta, no, sir. And you just showed that this exponential value has to be less than zeta. But sir, if this is less than zeta, then we can't conclude that probability of this will be less than this one, because both quantities less than zeta. So how can we say that this probability value is the less than this?
If A is less than B and B is less than C, what do you conclude?
So A is less than B and B is less than C, then we can conclude that A is less than C.
That's what I'm saying, right? This whole
this
thing,
one you assuming this above inequality.
This whole thing is less than zeta. That means this thing is less than zeta, right?
No, sir. If you assume the above inequality, then yes, sir.
Which one?
It's okay, sir. So this one that we have derived, sir, for the
this one.
No, above this one, sir.
This is
probability
true,
of the
right?
average.
We have derived.
Yeah, that's yes,
so
sir.
if
Yes,
upper
sir.
bound, I further upper bound it.
Yes, sir. I get it.
Questions?
Yes, sir. I got it. Sir.
Okay. Now I'm saying probability of this greater than delta is less than zeta, right? Provided the number of samples is greater than this. I can write it in a slightly different fashion, okay? Theorem. I'll write it as a theorem, okay? This is the proof is something that we have already looked at. Yes?
Hello?
Yes?
So that means if we increase the sample, our probability of the deviation gets smaller and smaller.
Correct.
Okay.
Smaller and smaller. Then with a probability of at least 1 minus zeta, the following holds, okay? What is that? 1 by n summation I equal to 1 to n xi is less than delta, right? Provided n, the number of samples, is greater than or equal to 2 sigma squared by delta squared ln of 1 by zeta. Okay, so this delta is something that I took delta to be something, so it's okay. Okay, is this fine? But this n is the number of samples, so I need an integer, so I'll seal it. Okay, is that fine? So essentially I'm saying this event happens with a probability of at least 1 minus zeta if the number of samples is greater than this many. Okay, is that fine? So if you are estimating the mean of a Gaussian random variable, you know what the number should be, right? You agree?
Yes, sir.
Okay.
That should not exceed.
Yeah. So is this fine? So this is well in the machine learning literature, this is called the pack bound. For those who are interested, you can just take a look at it. Okay. Right. So let's move on. Let's look at a very important concept in probability, which is the law of large numbers. Well, we have been looking at this now, but we will make it more precise. Law of large numbers. Okay. So, in layman terms, what this says is that if you have several instantiation of independent quantities, if you average them, the average turns out to be deterministic. That's what it says. Okay. So let's look at what is happening. What will happen if, for example, if you look at this result, suppose I replace these xi, x1 through xn by IID, not necessarily Gaussian. It can be any distribution with certain mean and variance. Okay. Let's see what is it that we will get. Okay. Yes.
Sir, I have a doubt. Like,
Yes.
can you go up? Sir, where the place where you have differentiated the supremum?
Okay.
Here you have
Yes.
differentiated and then differentiated. Sir, even if this is the differentiation of the, like, if infimum is there and we differentiate it, then also we will get the same result.
Yeah, you get the same result. Exponentiation is monotone, right? See, if you are taking supremum over all x, g of f of x, where g is monotone, it's same as g of supremum over all x f of x. So instead of solving the original problem, we can solve supremum over all f of x instead of supremum over all g of f of x. Okay? It's called monotonicity property. Very intuitive, right? But it can be proved. Okay. Is this okay, or shall we move on?
Yes.
Let x1, x2, etc., xn be IID with mean expected value of x1. Let me call this as x bar. It's same as expected value of x2 and so on because they are ID, and finite variance sigma square. Okay, let's assume this. Now let's see the following. So suppose I have probability of 1 by n summation I equal to 1 to n xi minus the expected value of x1, or I'll call it as x bar. Okay, greater than epsilon. What can you say about this is the question, right? What can you say about this one?
So we can apply Chebyshev's inequality.
You can apply Chebyshev's inequality. So that means I can just do the following, right? So probability of, I'll square on both sides. Greater than epsilon squared, right? So consider, okay, I'll just write this epsilon greater than 0. Okay, so now I can apply Chebyshev, right? What is the Chebyshev's inequality? Is less than or equal to, I have to apply the Markov for this, right? 1 by n summation I equal to 1 to n xi minus x bar whole squared divided by epsilon squared. Okay. Now I can write this in a slightly different fashion. Okay, so let me write this in a slightly different fashion. So expected value of 1 by n summation I equal to 1 to n xi minus x bar whole squared 1 by epsilon squared. Is this fine, everyone? X bar is a constant, so if I pull that inside the summation, it will be n times x bar. N and n cancels and you get x bar. Fine? What can you say about this? Suppose I call this random variable yi. What will be the mean of this random variable?
0.
Clear, right? Because expected value of xi minus x bar is what you get, but expected value of xi is nothing but x bar. X bar cancels and we'll get 0, right? Okay. What will be the variance of this thing? Sumit, can you tell me?
So we have to calculate, sir.
Okay, calculate and tell me what is the variance of yi.
Summation, expectation of
Everyone else also try, but if you know the answer, that's okay. But you can try. Hopefully, by that time, Sumit will be done. So,
Sir, can you tell me what is x bar in the statement?
x bar is the mean of xi or x1.
So that means expectation of x1 equal to expectation of x2 equal to
Yeah, because IID, right?
equal to x.
Because IID. Yeah, true. Not just expected value, everything, all the statistics will be the same, right? All moments. What will be variance?
So it will be variance of xi only. Variance of xi only because x bar is constant.
Sumit, you got it?
No, sir.
Can you try?
Why? Yes, I am doing that, sir.
What is the definition of variance?
Sir, expectation of y minus mean whole square, sir.
What is the mean here?
0, sir.
0. So what will be the variance? Expected value of
Expectation
yi
of
squared.
y square,
I
yes,
squared.
sir.
So what will be expected value of yi squared? What is yi?
X minus xi.
X minus xi? No, xi minus
Sorry,
x
xi
bar.
minus x bar, sir. Xi minus
What
x
is
bar.
this?
Oh, this is the variance of xi, sir.
Exactly, right?
Yeah.
Xi itself whole square, which is nothing but sigma squared because it's same for all. Okay.
Yes, sir.
So
Yes,
you
sir.
are adding a bunch of IID random variables with mean 0 and variance sigma squared and squaring it. Okay. I can write this in the following way. Okay, n epsilon squared expected value of summation over all I equal to 1 to n xi minus x bar whole square. Okay, fine. What is this? Okay, now it's basically algebra. Okay, so now what is summation ai whole square? What is a plus b plus c whole square? It's k square plus b square plus c square plus 2ab plus 2bc plus 2ca, right? And similarly, a plus b plus c plus d whole squared is what? You have a square plus b square plus c square plus d squared plus what do we have? You have all kinds of combinations, right? A, B, A, C, A, D, B, A, B, 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 A, B, C, B, D, and so on, right? So I can write this in this fashion. Do you agree? I equal to 1 to n xi minus x bars whole squared. This is like summation ai over all I ai squared. Then summed over all I not equal to j xi minus x bar into xj minus x bar. Is this fine? Are you guys convinced with this? Yes or no?
Yes, sir.
Yes,
So
sir.
this is nothing but 1 over n epsilon squared. Expectation is linear, so the first expectation I can pull this inside. So it will be expected value of xi minus x bar whole squared, which is nothing but variance. Right? I not equal to j, expected value of xi minus x bar into xj minus x bar. What can you say about this? This
Covariance.
covariance. Okay, but what is the answer? Tell me the number. It's a
0.
number. 0. Why?
It's IID, yes, 0, 0.
Yeah, so xi and xj are independent, right? Because I not equal to j, and xi minus x bar and xj minus x bar will also be independent. So if you have independent random variables, expectation of product is the product of expectation. So it will be expectation of this plus expectation of this. So if this goes to, this will be 0. Everyone understood this?
Yes, sir.
Okay. So now, what do we have here? Hey, did I make a mistake? I think I made a mistake. This would be n squared, right? N whole squared. N squared. Okay. So now we have n squared epsilon squared. You have n times sigma squared, which is nothing but sigma squared by n epsilon
In
squared.
epsilon square.
So this implies what? Probability that 1 by n summation I equal to 1 to n xi minus x bar greater than epsilon is less than what? Simple Chebyshev says n epsilon squared. So this goes to 0 as n goes to infinity for every epsilon greater than 0, right? So that means the probability that, so your, okay, the way to look at this pictorially is as follows. X bar is here, right? And your estimate, let me call this as, okay, so let me just change the notation a little bit. Okay, so I'll call this as mu and this as mu n hat. Okay, so mu is here, mu n hat. So I put a small interval around this, okay, whose width is epsilon, right? So the probability that your mu n hat falls in this as n goes to infinity is 1. That's what it says. That means the probability, so this essentially says that the probability that it falls outside goes to 0. That means the mu n hat falling inside should go to 1. That means you will be damn close to the actual mean when you have enough number of samples. That's what it says. Okay? Is this
So
fine?
what is the implication of mu n hat? I didn't understand that. That is, we can calculate mean of every individual random variables, and then we are averaging the random variables.
No, it's not the, so I want to find the bias of the coin, right? Bernoulli random variable 0, 1 with bias p. So the mean of that is also p, right? So how do you compute an estimate of p? You toss the coin 1000 n times, count the number of heads divided by n, right? That's like 1 over n summation xi, right? That's what you are doing. So what are the chances that it will be close to p as n goes to infinity? In fact, the chances go to 1.
Hello, sir.
Yes.
Sir, is it like P tilde and P?
Yes, it is p tilde and p. Yes. It's p tilde and p. Is that fine?
So yes, sir.
That means if it says that if you have enough number of samples, if you compute a sample estimate of the mean, that will be very close to the true mean with very high probability. That's what it's saying. Okay. But you need to have enough number of samples. In fact, as n goes to infinity, you will be very close to the true mean. Okay. Is that fine?
Yes, sir.
Maybe I'll define something and then we will look at the formal implication of this. Let xn be a sequence of random variable. Okay. I'm not saying it should be IID. Okay. We say that xn goes to x in probability if probability of xn minus x greater than epsilon goes to 0 as n goes to infinity for every epsilon greater than 0. You understood what I'm saying? Is this clear? So notation for this would be xn converges to x in probability. Okay, this is the notation that I'm going to use. Okay,
So that means we just have to do more and more experiments to. So that means we have to do more and more number of experiments to reduce the probability, like to get the actual P.
No, this definition doesn't say anything. This is a definition, right? We say that Xn converges to X in probability if the deviation greater than epsilon. That means it's a bad event, right? Whenever the deviation is more, you say that it's bad. So the probability of the bad event goes down to 0 as n becomes larger and larger. That's what it says. Okay?
Okay, sir.
Okay, now let's go back to this. So let me, again, sorry for using one more notation. So let me call this as Sn, okay? Right? Is that fine? Or, okay, let me not add notations, extra notations. Let me stick to the previous notation itself. Oh my God. Something is happening. That's why I hate Windows.
So I think you need to update, because I am seeing your update is a long due from the first lecture.
Yeah, true, but I don't want to update, but because I was told it screws up something else, so. Oh my God. Oh my God. Anyway, so I think I lost a lot of things, but I'll just write this definition, okay?
Sir, it is something like, sir, convergence of a sequence that we.
Huh?
It is, sir, just like a convergence of a sequence, no, sir?
Correct, correct. Let me just write this and get back to you. Xn converges to X in probability if probability of the deviation, which is Xn minus X, which is the error, being bad, goes to 0 as n goes to infinity for every epsilon greater than 0, right? So notation would be Xn converges to X in probability. Okay. Yeah, you were saying something, Sumit.
Yeah, sir. I think it is something like a convergence of a sequence, sir.
Yes, it is a convergence of sequence, but not
Yeah,
sequence of
exactly.
numbers,
Yeah,
but it's a sequence of functions or
yes,
random
sir.
variable, right? Random
Yeah,
variable.
yeah, sir.
Yeah.
Hmm.
For those who are studying, will be studying measure theory, this is called convergence in measure. But in this
Yes,
case,
sir.
it is convergence in probability measure
Probability.
because it's probability. Okay.
Okay, sir.
So let's look at that. The previous example, I'll say recall. Probability that 1 over n summation I equal to 1 to n xi, this is your sample mean, this is your true mean, greater than epsilon, goes to 0 as n goes to infinity for every epsilon greater than 0. So this is what we proved, right? Let's put this in context of this. Xn minus x. So in this case, Xn would be this, right? Summation over all n xi, right? Minus x would be same as expected value of x1. See that this x is a random variable here, but expected value of x1 is a trivial random variable, which is a deterministic number, right? You can think of that as a random variable also. So that being greater than epsilon goes down to 0. So therefore we have proved the following theorem, right? Let x1, x2, etc., xn be IID random variables with mean expected value of x1 and variance sigma squared less than infinity. Okay, then 1 by n summation I equal to 1 to n xi converges to expected value of x1 in probability. Is that fine? This
Yes, sir.
particular result is called weak law of large number. Okay, it's called weak because there are stronger versions of law of large numbers that will imply this particular law of large numbers. But this is very restrictive in the sense that we need finite variance for this result to hold good. What if I have a sequence of IID random variables but with finite mean infinite variance? Then whether this holds good or not, the answer is yes. But how do you prove that? Any idea? Hmm? Any idea? No?
So can
Yes.
you state once more? Finite
So,
mean and
finite mean and finite variance results in this theorem. But what if the variance is infinite?
so the mean is finite, right?
Mean is finite. Let's assume mean to be finite. Of course, if mean is infinite, then this average will also be infinity. So there is nothing much to do.
So in Markov, the mean comes in the numerator. I don't.
Fine, but how do you prove that this convergence happens? If the variance is, see, the key idea in proving this, right, was to apply Chebyshev. Chebyshev required variance, right? There was n sigma squared that we wrote, right? So if sigma squared is infinity, you cannot apply that, right? What do you do?
We take other moments.
Oh, if the variance itself is not there, I don't think you can talk about fourth moment, for example, right? You agree?
Yes, sir.
Okay,
Maybe
now
divide by variance.
your
Something.
variance is infinity, right? How do you divide by variance?
Okay.
Okay, think about that. I don't want to answer. So I won't even answer this in this particular course. There is a method called truncation to prove all these things. So maybe those who are interested can go through that. Okay. So this is the first very important result in probability theory called law of large numbers. It turns out that you don't need this. Okay. Don't need this. Need this in general. Okay. You only need this in under special conditions, special cases, not in a general scenario. Okay. Is that fine? Okay, I'll stop here, but if there are any questions, I can answer. We have 2 more minutes. Let's see if you have any questions. I'll try to
Sir,
clarify. Yes.
I have one generic question. I don't know
Okay.
if it's a question or not. So, like from the very starting lectures and others, we are taking like x1, x2, some random variables, and we are taking that Sn special type, like the summation of random
Correct.
variables x1 plus x2. So
Correct.
is there any special implication, or is it lead us to process some stochastic process or something?
No, so there are several reasons. So generally, what we need is the averaging, right? So, for example, if you are doing some estimation or you are doing something else, so typically you do averaging, you compute averages. So that's why that quantity becomes very important. And it was natural to look at those quantities rather than some complicated functions. Do you agree?
Yes, sir. Yes.
Okay,
Yes.
so that's why people started looking at these things.
Okay, sir.
Okay, so it need not be IID, it needs to be independent. Well, okay, so since you brought this up, maybe I'll ask you this question. So I have x1, x2, etc., xn, IID. Finite mean and variance, sigma squared less than infinity, expected value of x1 less than infinity. Okay. Now, I take the following sequence. And divide by n. What can you say about this? Are they IID? For example, this and this, are they independent? It's x1, x2 plus x2, x3. x2, x3 and x2, x1 are dependent, right? Because there is x2 common. Do you agree?
Yes, sir.
So now, what do you think is law of large numbers? It turns out, can you make a guess? Can you make a guess? Can you guess what will be the okay, what can you say about this? Okay, somebody can answer quickly. Hey, Ayush, you should be able to answer.
So this one is x1 square plus x, like summation of x1 square and x2 square and like that.
No, it is x1, x2 plus x2, x3 plus x3, x4 and so on, right? Hey, this was an exam problem in the course that you took.
So,
Right? Yes.
sir, I have one question, sir. Like, sir, you sometimes you say that independent and sometimes IID. So, sir, in case of proving, suppose we have two random variables, x1, x2, and I have to show that they are IID. So, in that case, we have to show first that they are independent, and then I have to show that their distribution function will be the same.
Correct.
These two, no? So, sir, how can we show like their distribution function is same? Like
Okay.
by any examples, sir, if you can show me.
If the two distributions are same, well, typically in theory, right? So we assume the distribution and then we move ahead. Okay. So if you want to show that, for example, if you have samples from two distributions, right? Now the question is whether they are same or not. That's what you are asking, right?
Yes, sir.
So one way is you just compute different moments. I know how to compute the mean, right? It's summation
Yes,
xi
sir.
over n, right?
Yes, sir.
What will be the estimate of variance? I know how to compute an estimate of variance.
Yes, sir.
Third moment, fourth moment, fifth moment, sixth moment, and so on, right?
Yes,
So
sir.
see whether those moments match. If all the moments match under certain regularity conditions, you can say that the two distributions are same.
Okay, sir.
So in practice, right, Sumit? So you
Yes, sir.
don't match all the moments. Maybe some fourth moment, if you match, you are pretty much done. So both the distributions are approximately the same.
Okay, sir.
Okay, that's all.
Yes.
Independence, testing whether two distributions are independent or not, right?
Yes,
That's
sir.
what we are
This one is easy, sir.
So that also again, you need to see, one way is you just have to compute the joint distribution again empirically,
Yes, sir.
compute the marginals and see whether the product is equal to the joint.
Yes, sir.
That is the test. Okay, you can come up with efficient tests for that also. There are efficient
Okay,
tests for
sir.
deciding whether two samples from two distributions are independent or not.
Okay, sir.
Okay, these are very well studied questions in statistics. Okay,
is
so
it
the answer is
mu square, sir?
sorry.
Sir, this was a mu square, I thought.
Okay, that's correct, right? Why? Because this and this are independent, this and this are independent, and so on. I can split the two into two sums of independent random variables. Each one will go to something, so I can just use that, right? Fine. Okay. Is that fine? We will see some of these things in more detail later on. Any questions? Himanshu, I don't see you speaking.
Yes, sir.
I said I don't see you asking any questions, participating in the class. What's happening?
Last few classes I missed, sir. That's
Why?
I had fever, sir, viral fever. So just I recovered.
Okay, I mean, if you give medical reasons, I can't say anything. But generally, your participation has been not so very active. Okay, so I see Rishabh, Sumit, and Praveen and Ayush Agarwal being, at least they're active and they ask questions whenever they want to. But I think Nitish and Jayant also very very rare, and Himanshu is almost even attending class. Well, you also.
Not like that.
Hmm?
I will ask her whenever I have.
Okay, so yeah, so please be attentive, ask questions. Okay, this is not a
Yes,
typical undergrad class, so slowly the difficulty level will go up. Okay, it becomes more and more challenging as time progresses. It won't be this easy. Okay,
Yes, sir. Yes.
if you find this difficult, then by the end of the course, it will be 10 times more difficult than this.
Yes, sir.
Okay. So, Rishabh, you had questions?
So not questions, sir. Actually, I was asking this time, as the course has been started after 1 month, so it will be extended also in December, right?
I think so, yeah. Yeah, it will go until December, don't worry.
Okay, sir.
Those things, don't worry. How many courses have you taken, Rishabh?
So 3 courses.
3 is three including what? Which are the 3 courses?
So linear
This
algebra.
mathematics. Okay, man. So good. So 3 you can manage.
Yes.
Okay. Okay. So yeah, Sumit.
Yeah, sir. Actually, sir, what should I do for the TA work, sir? You just mailed me, or so you will mail?
No, I'll mail you. Okay. So I forgot to do that. So I'll do that now.
Okay, sir.
Praveen, you are in the Nitish, you are in the, no, not this. Jayant, you are in the TA category, right?
Yes, sir.
Were you assigned any course? I mean, did your advisor talk to you about the course?
No, sir.
No?
No, sir. Rajshekhar, but sir did not say.
Rajshekhar Bhatt, right? I'll put you in DSP or something. Okay. I'll talk to Rajshekhar. Nitish, you are in Arya, right? Oh no, you are in CSR. No, you are not Arya. Yes, tell me, Nitish. Where are you, man? So Majestic.
Hello.
Yes.
Hello.
Yes, I can hear you. Tell me.
TA works software engineering, sir.
Hey, which department? Sorry.
Hello.
Hello. You are under whom?
Nikhil Hegde, sir.
Nikhil Hegde. Okay, good. Fine, no problem. Okay, I think Ayush is PRML. Sumit is for this. Jayant, I'll talk to Rajshekhar, right? Okay, fine. Yeah, thanks. Yeah, that's it. I think Savan, can you stay back? Others can leave if they want.
Yes, sir.
Yeah.
Okay, sir. Bye, sir. Thank you.
Yeah, bye. Thank you.
Bye, sir.
Yeah.
Thank you, sir.
Yeah, thank you.